Hi, welcome to another video on enzyme kinetics. In this one, we're going to look a little bit at enzyme inhibition. So to motivate this, let me introduce you to an enzyme called succinate dehydrogenase. This is an enzyme that's found in the inner mitochondrial membrane. It's part of the Krebs cycle. Some of you may recognize this. It's a complex protein with 4 different types of subunits. So this is the structure of succinate dehydrogenase. What we have here is the membrane. So it's actually embedded in the membrane. You can't see well here because it's in gray, but there's one subunit here, there's one subunit here, and there's 2 subunits in here and here. So there's 4 in all. Now this enzyme is an important one, obviously because it's part of the Krebs cycle, and it catalyzes the conversion of succinate to fumarate. Okay, if you look carefully at the succinate, it's and the fumarate for that matter, they're completely symmetrical molecules. So 2 carboxylic acid groups on either side, and then there's CH2 in the middle. What's happening here is the enzyme will oxidize the succinate to fumarate by creating a double bond in the 2 central carbon atoms. Okay, so this is an oxidation. Now, there's another molecule called malonate, and I've got it here. If you look carefully, malonate and succinate, so remember succinate was this one. Malonate and succinate are actually quite similar looking. The only difference is that malonate only has 1 CH2, whereas succinate has 2. Now, it turns out that the malonate is so similar to the succinate that it'll actually fit into the active site of succinate dehydrogenase. All right, so I've got a diagram here. So this is the enzyme with the active site. Succinate can bind to form the succinate enzyme complex, and that releases to form fumarate and free enzyme. Now, things go wrong if malonate binds, and malonate can bind because it is so similar to succinate, but when it binds, you get no product formed. Okay? And so if you had a mixture of succinate and malonate, you'd find that the reaction would actually slow down, because some of the time the malonate occupies the active site so that succinate can't get to it to form fumarate. And of course malonate results in no product. Okay, so as I say here, when malonate binds to the active site, it means that succinate cannot bind. This means the reaction slows down. This is an example of a competitive inhibitor. Right? So malonate is an inhibitor, and it does so by competing with succinate for the active site. The key thing is, of course, that malonate doesn't result in any product. Only succinate results in the product fumarate. Now we're going to cover in the next few videos. In this video, we'll just cover competitive inhibition, so this kind of inhibition. But there are other kinds, and the 3 main kinds you'll learn about in biochemistry or enzyme kinetics are competitive inhibition, uncompetitive inhibition, and non-competitive inhibition. I've always found these terms difficult to remember because they're so similar to each other, but we'll see if we can find a way to remember them in the next few videos. Anyway, competitive inhibition, uncompetitive inhibition, and non-competitive inhibition. The previous slide I showed you there were 3 kinds of inhibition we'll look at: competitive, uncompetitive, and non-competitive. All 3 kinds of inhibition can be represented by this generalized inhibition model. This is the Botts-Morales scheme that was devised in 1953. And you can get all 3 kinds of inhibition and more actually from this scheme. So in this scheme, I is the inhibitor, ES the enzyme substrate complex, and ESI the enzyme substrate inhibitor complex. Now I haven't included everything here because it gets a bit cluttered, but when E, so this is free enzyme, gets converted to enzyme substrate complex, there's a substrate here which I've not included that gets added to E to form enzyme substrate complex, because eventually it breaks down to enzyme plus product. It can also bind inhibitor, which again I don't indicate here, but you have to imagine an inhibitor coming in here, binding to the enzyme, forming the enzyme inhibitor complex, and of course this could be binding to the active site. There are other 2 possibilities here. maybe the inhibitor doesn't bind to the active site, maybe it binds elsewhere, in which case substrate can still bind, but this time we form the enzyme substrate inhibitor complex. And if we have this state, it could lose the inhibitor molecule and just end up as enzyme substrate complex. Now both these complexes in principle can result in product. In the first case we get free enzyme released, in the second case we get enzyme inhibitor released. Okay, so let's look at these in more detail. So what I didn't say in the last video what these symbols were. So these are the dissociation constants. So Ki is the inhibitor dissociation constant with respect to free enzyme. Km, which I'll call it Km here, is the substrate binding dissociation constant with respect to the free enzyme E. Okay. Now you'll be wondering that I've put Ki here as well, and I've put Km here as well, except they have an A in front of them. This is a factor, okay? And you're wondering why I can put Ki here and Km here, even though they look like completely different reactions. Well, what we have here is a cycle, right? A cycle of reactions. And in any cycle of reactions, the total energy change from, let's say we start with free enzyme, and we go all the way around back to free enzyme, the net energy change should be 0. If it wasn't 0, we could make a perpetual motion machine. And so these two halves should be roughly identical in terms of the dissociation constants, except changed by a factor. So that's why I can put the Ki here and here, but multiplied by factor A, and I can put the Km here and here, multiplied by factor K. All right. Now, the other factor is this B factor. Okay, so we've got two ways to produce product, in principle at least. And they could be different in the rate at which they release product. And that's what this B factor is for. So if B equals 1, then both are equally good at producing product. If B is 0, if this B is 0, only this step can produce product. And if B is less than 1, which is something we're not going to, we are going to consider it. If B is less than 1, then that means this state is less active than this and it produces less product. Okay. Now, as I said before, the factor A, this factor A represents the difference in binding affinities between the binding of substrate to the enzyme inhibitor complex and binding of inhibitor to the enzyme substrate complex. Now, if A is 1, there's no difference in binding. They're identical. Okay. Now, if A is increased, the equilibrium to enzyme substrate inhibitor complex is less and less favorable. And in the limit, there's no enzyme substrate inhibitor complex at all. So if A is much greater than 1, all right, let's make A much bigger. That means that there'll be less and less of this. We'll see this in a minute when I show the equations, but it means it'll be less and less of this. In fact, in the limit, as A goes to infinity, we basically just get that portion of the scheme. Note that if I eliminated the entire bottom half of the scheme, I end up with a normal Michaelis-Menten mechanism. Okay. Now, the reason for going through all this is that the factors A and B, you can change them in whatever way you want, and in changing them, you'll get all the common inhibition models. In fact, although we won't consider it here, you can arrange it so that the factors also produce activation models, and the inhibitor is no longer acting as an inhibitor but is acting as an activator, but we won't consider that here. Okay, so now what are the different ways that we're going to look at in terms of combinations of A and B? Well, remember in the previous slide I had 3 kinds. I had competitive inhibition, non-competitive and uncompetitive, and here I list them here. So this is a sort of tree chart or sort of a taxonomy of inhibition when B equals 0. So I'm not going to consider this step at all, but this is the model we're going to look at. There's an entire separate tree to the right that includes this step, but we won't include that here. So in this tree, which is called complete inhibition, when B is 0, we'll have pure competitive, uncompetitive, non-competitive, and of that there are 2. Now the non-competitive is where the inhibitor only binds to free enzyme. So it's basically that. Okay, and that's the competitive inhibition model we saw earlier. All right, so we can represent this as this kind of shape. Now this happens when the factor A is much, much larger than 1, which you've seen before, and that basically means that the equilibrium concentration of enzyme inhibitor substrate complex is virtually 0, and so it basically disappears. Okay. Now the other case is when the Ki is much greater than AKI. When that happens, so when Ki is very big, we get hardly any enzyme inhibitor complex, and so we're just left with this portion, and so we get a T shape. Now then we can get a blend of both of them, right? We get a blend of both of them when either A is equal to 1, so we get basically the square. That's called pure non-competitive, or A is only a little bit greater than 1, in which case we get this mixed. Okay, so the strengths of the two arms are slightly different. Okay, so we get pure competitive, uncompetitive, and then non-competitive, which can either be pure or mixed. Okay, now in this video we're only going to consider pure competitive. All right, so let's look at this competitive inhibition model. Right, so this is the case here. All right, the enzyme substrate inhibitor complex is gone. We're just left with this shape. Right, it's sort of upside down L. Okay, and this is the case when the factor A is much greater than 1. And to go back to that, you may be wondering, why is it so important that A is greater than 1 for this case? Well, if A is much greater than 1, let's think of this for a second. If A is much greater than 1, then the complex in the denominator has to be very small. All right, so if the complex is very small, then we have basically no enzyme substrate inhibitor. Now these two are for these reactions, but if we wrote these for the remainder, okay, the bit that's missing, and added A in there, so when A is very big, the only way for this, if I had A in front of here, the only way for this to be very big is for this to be very small. Okay, so that's why when A is much bigger than 1, this bottom piece just disappears effectively. Okay, so now to derive the reaction rate for this model, we have to tot up the number of active states and the total states. So the active state is just ES. That means the state that produces product. Free enzyme doesn't produce product. Enzyme inhibitor complex doesn't produce product. Only ES produce product. So in the numerator, I have to form this fractional saturation. In the numerator, I'll put ES. And in the denominator, I'll put all the states. And there are 3 states: free enzyme, enzyme inhibitor complex, and enzyme substrate complex. Okay, so this is the fraction of all 3 states that's in active form. All right, and it's the active form, of course, that produces the reaction rate. Okay, so here I got the fractional saturation again. Now what I'm going to do is I'm going to take these equations here. Okay, so this was the Km and the Ki is this one. Okay, I'm going to take these equations here and move ES onto one side, move EI onto one side. Then I'm going to swap this ES here with this one, and then swap this EI here with this one. When I do that, I get these ratios. Okay, so now I multiply top and bottom by Km, and I end up with this. I cancel out the E's as well. All the E's cancel, right? Cancel. And I end up with just S, the substrate concentration, I, the inhibitor concentration, and the 2 dissociation constants, Km and Ki. Now, we're going to assume that the reaction rate is proportional to the fractional saturation, which seems reasonable. Remember, the fractional saturation goes from 0 to 1. When it's 1, all the enzyme is present as enzyme substrate complex, and when it's 0, there's no enzyme substrate. So to convert the fractional saturation F into reaction rate, all I need to do is scale the fractional saturation by a constant, in this case called the Vmax, and I get the equation for competitive inhibition. So S is the substrate concentration, I is the inhibitor concentration, Ki and Km are the 2 dissociation constants. if you set I to 0, this disappears and I end up with that, and that of course is just the straight Michaelis-Menten equation. Okay, all right. All right, let's take that inhibition equation and see what it looks like when we plot it. So this is a plot of the reaction velocity versus the substrate concentration. I've set the Km to 4, okay? And this leftmost curve here represents the case when there's no inhibitor at all. As I increase the inhibitor the curve starts to get lower and lower and lower. Okay, so as I increase the inhibitor concentration, the curve basically just takes longer to curve up to saturation than it otherwise would. And that makes sense. As I increase the amount of inhibitor, there's more competition for the active site, so it becomes harder and harder for the enzyme to actually produce product. Okay. Now, you may be aware of this famous plot, the Lineweaverburk plot. There's a way to represent these kind of curves in a different way. So let me start off with the simple Michaelis-Menten equation. What I'm going to do is I'm going to take the reciprocal on both sides. So the reciprocal of V is 1 over V. I invert this expression and then pull apart the terms, and I end up with this. Okay. Now those of you who remember your linear equation will recognize this actually to be a linear equation. So B, of course, is 1 over Vm. The slope is Km over Vm, which is m, and x is 1 over s. So if I were to plot 1 over V versus 1 over s, I would get a straight line. And in that straight line, the y-intercept, which is this, is 1 over Vm, and the slope is Km over Vm. Now you can also work out the x-intercept, which turns out to be minus 1 over Km. So to give you an example, let's say I have some data. I actually made this up. What I did, I plotted the Michaelis-Menten curve, then I added some noise to the data points, and I then plotted the points, and I get this sort of data. So it rises and then reaches a plateau as it saturates, and so this looks like real data. I'll take each data point, work out 1 over V, work out 1 over S, and plot the point onto this graph. I do that for all the points, and I get the points scattered around here, and you'll see they seem to lie on a straight line. Okay. Now one thing you may notice is that they seem to spread out. They seem to scatter more higher up the axis we go, and we'll come back to that in a minute. So the y-intercept here is 1 over the Vmax, and the slope is Km over Vmax. Now we can do the same thing for the competitive inhibition. There's a mistake there, I'm afraid. We can do the same thing for the competitive inhibition equation, which we had before. And again, all I'll do is I'll take reciprocals on both sides. So the reciprocal of this becomes 1 over V. The reciprocal of this, basically invert the equation and pull out the terms, and I end up with this. Now when I is 0, this basically just disappears, and I end up with what I had before. All right. Again, though, this is a straight line. Okay. Here we have the slope. That's the y-intercept, that's x, that's y. Okay, so the slope is Km over Vmax times that term, and then the y-intercept is 1 over V. Now what's interesting here is that the y-intercept is unaffected by the inhibitor, and the inhibitor term only appears in the slope. Okay. Now what can we say about the slope? Well, if I increase I, okay, and I'm adding this term onto 1. That means this whole thing gets bigger, so the slope gets bigger. So if we had a straight line, I mean, this will produce a straight line, and I increase the amount of inhibitor, the line will start to get steeper and steeper and steeper. Note, however, the y-intercept remains fixed. Now you can also look at this term here, this piece here, as a sort of super Km. We don't call it a super Km, we call it an apparent Km, okay? And if I were to replot, you saw this plot before where I plotted the rate against the substrate concentration at different levels of inhibitor. If you recall, at half the maximal rate, so that's here, if I take that and draw a line right across the curves, every time they intercept, that's the Km for that line. And you can think of these as the apparent Kms, Okay, so that's the actual Km because that's when I is 0. But as I increase I, the apparent Km appears to increase. Of course, what's actually happening is the real Km stays the same, but this term in brackets starts to increase. But often people will call this the apparent Km. Now you'll notice that these look all bunched up here, right? And it's maybe difficult to see what's going on. The reason I did that because I wanted to see that the lines would converge or converge to the saturation point at high substrate concentration. Now that's a bit awkward. I want to see things going on down here, and I want to see things going on up here at the same time, and it's not really working on this graph. So the way to deal with that is to, instead of plotting things on a linear graph like this, linear scale, I'll plot it on a log scale. So let's see what happens when I plot that same graph on a log scale. So now the reaction rate is on a log scale. The substrate concentration is on a log scale. So they're going up in factors of 10. Okay, 0.1, 1, 10, 100, 1,000. And now you can see things are much more balanced. Things all saturate together, which is nice. And it's not too far away from where the Kms are. So these points here, the same ones I had here. Exactly the same ones, except they're in black now. Now half the maximum velocity is not exactly halfway anymore, because if you're on a log scale, it's actually up here. Okay, so that's that should be 0.1, 0.2, 0.3, 0.4, 0.5. So that's 0.5. That's half the reaction rate. If I draw a line across here, right, at the end, when the line intercepts the curve, I drop a perpendicular, and that's the Km. So these are the apparent Kms, and you see the apparent Kms increase as the inhibitor increases from 0 to 50. Right, so that's, this line is at 0, this line is at 6, this line is at 16, this line is at 50. And doing log plots like this is actually quite a nice way of illustrating the effect of a competitive inhibitor. For a start, notice that the maximum rate doesn't change. And as I said before, the y-intercept is 1 over Vm, and that's unaffected by the inhibitor. So the maximum rate is unaffected, but the Km changes. Now another way to see that, which is probably the more common way of doing things, is to plot the Lineweaverburk plot again. Remember, it is 1 over V versus 1 over S. So the bottom curve, the bottom line, the straight line, is when there's no inhibitor. As I increase inhibitor, the slope of the line changes, but note the intercept stays the same. All right, the intercept stays the same because that's unaffected by the inhibitor. But the slope contains the Km term, and that is affected, and the slope increases. Okay. Now, I want to come back to the data. So this is the data I made up, and I plotted it on a Lineweaverburk. And you'll notice that the points tend to be bunched up at the bottom, and then they sort of spread out and scatter more as we go up the line. And this is one of the problems with the Lineweaverburk plot. It tends to estimate the intercept pretty well because everything is bunched down here, but the slope, because the points are so scattered, could be anywhere. All right, and we usually have to give ourselves a good guess where we think the slope is. And this is one of the failings of the Lineweaverburk plot. And when you do a Lineweaverburk plot, even on a computer, your error estimates on the Km will actually be quite wide. Not only that, when we're up here on the axis, right, that means S must be small. Right, so let's say S is 0.1, so 1 divided by 0.1 is 10, so we're up here. So up here means low S. Down here means high S. Right? Now it's much easier to do experiments at higher concentrations than at lower concentrations. At lower concentrations, we tend to make more mistakes in our experiments, and that partly explains why we have more scatter as we go up the axis. The other reason is that the 1 over V, I won't have time to explain this, but the 1 over V actually also distorts the error. And that also contributes to the extra scatter you see as you go up the line. So Lineweaverburk plots are great for doing things like this and saying, if I see that pattern, I know it's a competitive inhibitor, right? We've been looking at competitive inhibition. Competitive inhibition gives this pattern on a Lineweaverburk plot. What the Lineweaverburk plot isn't good at is getting you a good estimate for the Km. Now for that, I recommend doing something called nonlinear fitting, and I'll reserve a video in the future to show you how you can do nonlinear fitting for fitting enzyme data, and I'll also compare it with the Lineweaverburk plot and show you how the error estimates, especially for the Km, are really wide for the Lineweaverburk plot, but are not very tight for the nonlinear fitting. Okay, that's all for now.